Thanks, Ian. Okay, one more to go. I've packed a bit more into this talk, since you're probably all used to my accent now and things like that. And there's some background from some other talks which I can go over more quickly. Okay, so let's see. I'm just going to run through some useful facts. You'll notice on the title here, it's the X-ray transform on projective space, and you might be wondering what that means. Does it mean complex projective space or real projective space? And it means actually both. I'm going to discuss the X-ray transform both on real projective space and on complex projective space. Here are some useful facts about real projective space and complex projective space. So first of all, the curvature on real projective space looks like that, suitably normalized. So G is the usual round metric on the sphere, so induces the round metric on real projective space. And the fact is that when you look at the curvature tensor suitably normalized, then it looks like that. So that's another way of saying that the curvature is constant. This is a constant curvature metric. If you compare that with the corresponding formula on complex projective space, it looks rather similar. So this is the formula for the curvature on complex projective space of the Fibration metric. So on complex projective space, there are sort of two natural tensors. One of them is the metric, of course, and then the other one is the complex structure. But I've used the metric to lower the index on the complex structure, and in fact, that's how I'd like to think of it, as a symplectic manifold. So CPN is a real manifold. I'm thinking of CPN as a real manifold, and it has a metric on it, and it has a symplectic form on it. And if you work out what the curvature is in terms of that metric and symplectic form, which are the only natural ingredients that you have, then it's this. Again, suitably normalized. There's not actually much choice about what you can write down. This is the only tensor that you can write down in G's, which satisfies the Bianchi symmetries. This is that. And this is the only tensor, these three terms here, is the only tensor you can write down in J's, which satisfies the Bianchi symmetries. So the only content of this is that actually the constant here is 1. Right, but there's a very close relationship between the two of them. And in fact, there are many ways of putting RPN inside CPN. First of all, there's the standard way. You just put Rn plus 1 inside Cn plus 1. That induces an embedding of real projective space into complex projective space, which generalizes, for the case n equals 1, it generalizes the equator sitting in the sphere. And just as the equator sits in the sphere, that is a totally geodesic embedding. In other words, if you have a geodesic inside Rpn, placed inside CPN in this way, then, well, the metric is inherited, and the geodesics stay within RPN. Right. And in other words, when you look at this, compare the curvature on CPN with the curvature on RPN, it really is the case that although these symbols mean different things, so this is the Fibrini-Studi metric, not the round metric, when you restrict from CPN to RPN, then this metric here restricts precisely to this metric. And the curvature restricts to the curvature. And the only thing that happens is that the symplectic form vanishes. And of course the symplectic form vanishes because this is a totally real embedding, and the symplectic form has type 1,1. So, okay, so everything's nice and consistent, in other words, between CPN and RPN. And these embeddings are useful. I'm going to call them model embeddings. One of these embeddings is the embedding I just said, the standard embedding, when you put Rn plus 1 inside Cn plus 1, and all the others are what you obtain by using the isometry group of CPN, right, which is SUN plus 1. Okay, so you can move these model embeddings around by means of isometries, and you get more things which I will call model embeddings. Okay, the next fact is the BGG complex on real projective space. What does it say? So I'm going to write out some of the actual consequences of the BGG complex in real money. Well, the first rather trivial one is that if you've got a one form, then it's closed if and only if it's exact. That's a global statement well, it's a local statement on real projective space, which is also true globally. Okay, so, but there's a generalization of that. There's this sort of thing. Suppose you want to know whether a symmetric tensor, so this is a symmetric tensor here, whether that is obtained from a one form by means of taking the derivative here. This is the round derivative, the Levitt-Civita connection with respect to the round metric, and then taking the symmetric part. Then, for that to be true, there's a condition which is if and only if, and it's a second order condition. This is the next operator in the BGG complex, and this is what it is explicitly. What it is you form this composition, and then you take pi of it. Pi here is the projection into the leading order part. It's the Cartan product. It's making it have the symmetries of the Riemann tensor, in fact. Okay, and there's a whole bunch of formulae like this. So it's fairly simple for one forms, then it gets more and more complicated. So these are some facts. This is what happens if you write out the BGG complex in real money, where real money means you're using the gadgets that you have on the sphere, namely the connection and the curve and the metric, and nothing else. Okay, and then there's some relationship between forms and tensors on CPN and the corresponding things on RPN. I'm going to explain a little bit more about this on the next slide, but for two forms, what I'm saying here is that a two form, if you restrict it to RPNs and you get 0 for all of these model embeddings, that's true if and only if this thing is actually a multiple of the Kähler form. So in other words, so I'm introducing some notation now, that this is equal to 0 only if and only if its trace-free part, that's what that means, but with respect to the Kähler form, is equal to 0. So this is a skew form, so it has two parts because we've got this skew J lying around, symplectic structure. So two forms break into two pieces, the part which is pure trace with respect to J and its trace-free part. And the corresponding lemmas well, I'd normally say lemmata, but the corresponding as another lemma for curvature tensors. So this is now suppose you have something which satisfies the symmetries of what's here on the right-hand side. So this is a curvature tensor. And suppose that has the property that when you restrict it to all of these model embeddings, you get 0. That's true if and only if the trace-free part is equal to 0. And now I'm going to explain that a little bit more precisely in terms of representation theory. Yes?
That's one for things with the appropriate symmetry and ABCD?
Yes, the thing, right, so the thing with the appropriate symmetry in ABCD, so Riemann tensor symmetries, has the property, and well, it's on the next slide actually. Okay, this is what it is in more detail. If you have a psi which is skew in its first two indices, skew in the last two indices, and satisfies the Bianchi symmetry, right, that defines an irreducible representation of SL whatever it is, the dimension. This is the Riemann tensor symmetries. Then when you restrict it to all of these model embeddings, then something happens. Okay, and if you write this out in terms of my favorite notation, which is this notation of writing everything out with Dinkin diagrams and so on, this will be the case n equals 4. The case n equals 4, you're looking on CP4, that's an 8-dimensional manifold. You're looking at tensors on an 8-dimensional manifold. That's the Dinkin diagram A7. Right, so it's got 7 blobs here. Putting a 2 there is precisely what encodes these symmetries. If you then, the representation theory way of saying it is if you then branch that to SP8, which is the natural symmetry group that you have, the natural structure that you have for symplectic manifold, which is how I'm thinking of CP4, then it breaks up into 4 pieces. Very much like the decomposition under the orthogonal group. So it breaks up into a part which is pure trace. This is the symplectic algebra, SP8. It breaks up into a symplectic part, a skew part, and a scalar part. Okay, and this bow tie means there's some sort of well, it's exactly, yeah. You know what I mean here, right? This means these bow ties here are just some algebraic combination of these things, which has the right symmetries. Okay, but this is how it breaks up abstractly. So you compare that with the decomposition of the usual symmetry tensor, usual Riemannian decomposition into the Wahl tensor, the trace-free Ricci tensor, and the scalar tensor. Okay. Sorry, what's what and what? Say again.
What's theta and phi?
Right, this is right. This is a scalar. So this is like this. You should compare this with being the scalar curvature, and this is a trace-free two-form. Right, and then there's some formula here which I'm suppressing by means of these butterfly symbols. Okay, and then the theorem is, like this lemma from the previous slide precisely says that if you have one of these gadgets, a tensor in the ambient space, whose restriction is equal to 0 for all these models, then this part vanishes. These parts can be anything. Well, you can see one way around is clear because every time you restrict to a model embedding, J vanishes. Right? But what I'm saying is that actually this characterizes things. Right? So you can ask yourself what happens more generally if you take a more general representation here. Right? It's not completely trivial. Anyway, this is a true lemma, and I'm not going to prove it at you. It's easy representation theory. Right, let me give you a little bit more detail about those BGG operators, some more detail about that other part of the first slide. I'm just going to first of all repeat what I had about a one form being closed or a symmetric two form here being the symmetrized. Suppose you go to the next one. What happens here? So for the next one, what you get is a formula like this. Okay, you get a 4 here. And these formulae actually become more and more complicated for higher and higher order. This one here, where you've got 3 indices, this is a third order integrability condition. This is second order, first order. The order keeps on going up. The pattern, so ... The pattern is actually a very interesting pattern. So the combinatorics so far, you see there's just the coefficients here are 1, 1, 1, 1, 4. The next one is 1, 10, 9. Then it goes more and more complicated things. Okay, and actually these, if you try and find these sequences on the online encyclopedia of integer sequences, they're not there. Some of them are. Actually, if you cross out every other row, you can divide this into 2 triangles, one of which is on the online encyclopedia, and the other one is not. And I do not know closed formulae. So if you want some instant fame, then I don't know closed formulae for these numbers. Right. Okay. So it's a little bit more complicated than one might imagine. Now, this is just background, and let me tell you now what the content of the talk is. Okay, so what I'm going to talk about, first of all, I'm going to talk about the Radon transform and the Funck transform on the sphere or the plane, respectively. Then I'm going to talk about the X-ray transform on real projective space, whatever that is. Then we're going to do it on complex projective space, on functions, one forms, something a bit more complicated, a small interlude on symplectic geometry before we do it on symmetric tensors, and finally some ingredients for how you prove all these things. Okay, so let's start with the Funck or the Radon transform. Start with the Funck transform. What is this? Right, so Funck's a real person. It's not just a sort of trendy name for even though it's a really, really nice geometric construction. This is named after Paul Funck. Okay, in 1913, notice, very early on. Right, so here's the picture. You have a function on the sphere. This is my notation for just being a smooth function on the sphere. So that's what f is. And here's the sphere. This is the 2-sphere. And here is a great circle, gamma. You can integrate this function around the great circle and get yourself something which depends on your choice of great circle. So you get from this, in this way, you get a function, you get a transformation from functions on the sphere to functions on the space of great circles on the sphere. Okay, that's the Funck transform. This is the Radon transform. The Radon transform, what you do is, well, for simplicity, let me start with a compactly supported function on the plane, and I restrict this to an arbitrary line. So gamma is now a line, and you integrate it, and you get now a function on the space of lines in R2. So the space of lines in R2. Right, this is in 1917. This is the one that people generally go on about when they talk about, well, they've got about medical imaging. Right, so inverting the Radon transform is trying to invert what's happening in a CAT scanner. Okay, so, right, but in fact, these transforms are the same transform. Right, so not everybody knows this. Well, well, yeah, okay, so they're actually equal, but in order to make them equal, in order to see that they're equal, you have to do a trick. So let me just tell you a little bit about the trick. And then once we know this, then everything I'm going to say applies equally well to the Radon transform as it does to the Func transform. Now the Func transform, if you have an odd function on the sphere, then the Func transform gives you 0, right? Because you're integrating it round a great circle and it's an odd function on the circle, its integral will be 0. On the other hand, what is the space of great circles on the sphere? Well, you can, if you pick a north pole for your sphere, that gives you an equator. Right? So you can parameterize the great circles by points on the sphere, but of course the north pole and the south pole give you the same circle. So interpreted in that way, what the transform is a function from, you may as well just restrict it to even functions since it kills the odd ones, and you end up with an even function on the sphere. So better, this is a function between real projective space. This is a transformation between functions on real projective space. And even better than that is that in order to make it sort of properly invariant and respect the group action, so here the group action, natural group action is SL3R, so the group of projective transformations. In order to make this projectively invariant, it's a good move to replace functions actually by sections with an appropriate line bundle. That's what that means. And similarly on the right-hand side. And it's even better to replace real projective space here by its dual, since that's the space of lines inside real projective space. So having made these corrections...
What does the tilde mean?
Yeah, so the tilde means that... so on real projective space, there are not just these bundles, but there's also the bundle which is corresponds to odd functions, whose sections would be odd functions. That would be E tilde with 0 here. Okay, so there's another bundle on real projective space whose sections correspond to odd functions on the sphere. Right, there's another character. So in real projective space, the group is disconnected. So there's another, the stabilizer group is disconnected. So you get another okay. Right, and now when you compare this, noticing that Func transform is you just put the usual affine coordinate to put R2 inside RP2. This is a projective equivalence. Right, so when you do this, lines here, which are what's relevant for the Radon transform, goes to lines here, which are what's relevant for the Func transform. Right, and then when you do that, well, at least you can put the compactly supported ones inside here. You can just trivialize this. Okay, so what you do, there's a particular way that you trivialize it so that you identify this with the function's homogeneity to be -2. And then when you do that, the Radon transform and the Func transform agree. Okay. Right, so that's Radon transform versus Func transform. And now, without further ado, I'll go in one dimension to the X-ray transform. So the X-ray transform I introduced, this is the one introduced by John, or Jon, in 1938. This is the one which integrates over lines in R3. Okay, so it's exactly the same thing, but gamma is a line in R3. So all I've done is replace R2 by R3. And as soon as you see this, you should better think of it as happening on real projective space. So on real projective space, you've got a function homogeneous to be -2, and you're integrating it around the geodesics. Okay, but you should think of this all as being projectively invariant, so that's what you're really doing. And really, the invariance, the real reason that this minus 2 is here, you can see this now, is because when you restrict to a real projective space inside a real projective line inside R1, then there's a almost canonical identity this with the one forms. And so this really is an invariant integral. This explains why this thing being invariant under SL2R makes this transform invariant under SL4R. Okay, so you get a good amount of symmetry when you do this, which is important for various considerations. Okay, so the X-ray transform on RP3, you should start with such a thing. Now on real projective space, and it ends up where? Well, the space of lines inside RP3 is the Grassmannian of two planes inside R4. Right, so when I wrote down the formula for the Radon transform a couple of lectures ago, I had some explicit coordinatization of lines in R3. But it's a four-dimensional space. This is a four-dimensional space, four-dimensional real space. And just in order to keep the gods of mathematics happy, I've written down the right line bundle here where it takes its values.
So this twist on the left, you don't really need that. You can just push it off without a different twist on the right.
No. You do need this in order to have SL4R preserving this X, preserving the transform. Yeah. If you change your mind about this twist, then it's still invariant under orthogonal transformations, but you lose the SL4R invariance. Okay. Right, so you can ask, what about the range of this operator? And I sort of gave you a differentiation under the integral sign argument that said that the range should satisfy some equation. And when you set it all up correctly, this is this has a conformal structure. This is a conformally invariant operator. It's indefinite signature, so its kernel is very large, and its kernel is exactly the range of this. And it's almost what John showed. So John showed the corresponding thing in the setting of R3, where you either say you have a function of compact support, or you have suitable decay conditions at infinity. If you compactify in this way, you can just ignore the decay conditions. Once you put it on the sphere, you're sort of tempted to use spherical harmonics to analyze this, and that's what Funk did. If you have it on the plane, however, you're tempted to use the Fourier transform, and that's what everybody does when they're looking at the Radon transform on the plane. Okay, but in fact, there's a bigger symmetry group which contains both of them. That's a sort of a simplifying feature, I believe, of this viewpoint. It enables you to prove things. Okay, so this everything here is now SL4C invariant. And you can ask, what about the kernel of this transform? And it's actually injective. So for n greater than or equal to 2. So that was actually shown by Funk. That was Funk's main result, is actually that it's injective. Okay, and he showed it by spherical harmonics. Okay, so as a Riemannian manifold, just invariant under SON rather than, you can just simply identify this canonically with the space of functions, no problem. Okay, and then you're reduced to the usual Funk point of view. Okay, when you look at the X-ray transform on CPN, it's exactly the same sort of deal. The point is that on CPN, again, just like on RPN, all of the geodesics close. Right, so here's a typical geodesic, gamma. It's just a circle. It closes. You start with a smooth function or something a bit more exotic on CPN. Gamma is a geodesic. You integrate the function over the geodesic, and you get a function on the space of geodesics inside CPN. And the questions would be, what's the kernel of this? Also, what about the range? But I don't know the answer to that, so I'm not going to ask that question. But I do know how to answer what the kernel is. What about integrating something a bit more than a function? A one form is actually the rather natural thing to integrate. That's the natural thing to integrate over curves. So you could ask, what about that? What about the kernel of that transform? And more generally, what about a symmetric tensor? So you could take a symmetric tensor on CPN, restrict it to your geodesics, right? Plug, if it's got valence k, plug k unit vectors into it to get a function, integrate around the geodesic. Right, that gives you a transform. What about its kernel? Okay. Right, here are some known facts. Okay, so this is just a repeat of what we already know for real. Well, Funk did it for the sphere, but you can get this one just by looking at spheres inside, or real projective spaces of lower dimension inside RPN. So as soon as you've got it for RP2, you have it for RPN. That if you've got a function whose integral along all geodesics is 0, then f is in fact 0. So you can relate this to the X-ray transform immediately for functions on CPN, because if you have the same sort of thing for CPN, then in fact for all geodesics inside CPN, you can arrange one of these RPNs, these totally geodesic embedded RPNs, inside CPN, which contains your given geodesic. So you can arrange a model embedding. Okay, so what you know is that this is actually 0 for all of your RPNs. And then you just read off what you know about RPN, and you conclude that, so it's the transform is pulled, yeah, the pullback of f to all of these model embeddings is equal to 0. And that means that f is actually 0. So f is injective on functions on CPN. Okay, this is not the normal way that people do it. If you want to look at a normal way that people do it, there's a proof by Helgeson in his book on the Radon Transform. Okay, so one-dimensional things. Only one-dimensional things here, yes. Only the X-ray transform. Yeah. High-dimensional, don't know how to do. Okay. In CPN, yes, in both CPN and RPN, you could be integrating over higher order things, but I'm not. Yeah, just ordinary, and CPN is just a real manifold from my point of view. Yeah.
The operator that characterizes the range expected
Yes. Well, maybe. Yeah, I know nothing. I know nothing about the range. Yeah. 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 Okay. Okay, so the approach to more general tensors, this is joint work with Hubert Goldschmidt, is exactly this picture. So you start with CPN with a geodesic inside it. That geodesic actually it determines a whole family of RPNs which contain that as a geodesic. So the picture is like this. Okay, and the aim is to exploit this picture in order to say things about the X-ray transform on CPN. Okay, so here we are putting a totally geodesic RPN inside CPN, for example, by means of the standard embedding, and then by moving them around by the isometry group, translates under the isometry group of the Fubini-Studi-metric, which is this. Okay, so these things, I just remind you, are called model embeddings. Okay, now the point is the X-ray transform on real projective space is well understood. Well, that's a claim. I mean, that's something I'm going to say some words about. The X-ray transform on real projective space is well understood. The pullback of tensors from CPN to RPN is well understood. That was what I was saying about this curvature lemma, what I called a curvature lemma. That's a typical result that gives meaning to this well understood. Okay? Not only that, but there are suitable global techniques on CPN, which I'm going to tell you a little bit about, compatible with the similar techniques on RPN. The techniques on RPN are called, well, examples of this BGG complex, examples of higher order integrability conditions. Okay, so that's the plan, that's the approach. And now let's run through that approach on one forms where it's reasonably familiar. First of all, here's a theorem about RPN, but this is part of actually some general machine. This is absorbed into a more general machine that can answer more or less any question you like about the Radon transform or the Funk transform or the X-ray transform on RPN. But in 1978, Michel proved that a one form is closed if and only if its integral around all geodesics is equal to 0. Okay, so that's the result for the kernel of the X-ray transform on one forms, on real projective space. Okay, so let's just run through and see how we can get from real projective space to complex projective space.
Is there anything to that proof
How does Michel do it? Well, you can do all of these things. You can do all of these things by expansioning spherical harmonics for low tensors. For high tensors, you don't want to do that, and I'll tell you something better you can do. Right, so the plan is, okay, so suppose you know that this integral is equal to 0 for all geodesics in CPN. Okay, then you know it for all these model embeddings. Then you read off from Michel that the conclusion is that if you take d of omega, so the omega is the one form on which you're operating to start with, d of omega, we want to know it's 0, but what really happens is that we only know that when you pull it back to any of these model embeddings, you get 0. Okay, that's what you know from there. The conclusion is, this was this sort of algebraic lemma that I was alluding to earlier, one of these two algebraic lemmata which I earlier alluded to, is that then the result is not that this is necessarily equal to 0, but it must be a multiple of the Kähler form, must be a multiple of the symplectic form. Okay, but now I claim that in fact that forces omega to be closed. In other words, it forces theta to be 0. Okay, that's what
you said and what you wrote is not the same thing.
it forces omega to be exact, yes, but it's equivalent to say that it's closed because the first Durham cohomology of CPN is equal to 0. Yes, sorry, I should have said that. Right. Okay, so let's see this. So you know, it's a rather trivial example, but on CPN, for one forms on CPN, the following are equivalent. This is first of all that omega is closed. Second of all that omega is exact. That's the other way around. Omega is exact. Omega is closed. Third of all that the trace-free part of omega is 0. And fourthly, that omega is a multiple of the Kähler form. C and D are trivially the same. I've just written them in two different ways. Right, so A and B are equivalent because some vanishing of Durham cohomology. C and D, that's just the definition. So now I have to show, let's see, B implies C is trivial because this is a special case of that. The other way around. Okay, what I'm going to do is show D implies B. All right, so you start off with D. You differentiate both sides, use the chain rule here, and what you get is that. So I'm using the fact that this symplectic form is closed, so just one term. But then this symplectic form is non-degenerate as well. This is only a one form. That actually implies that d omega is equal to 0. That implies that omega is a constant. Two possibilities, omega is either theta. Theta, this constant, is either 0 or non-zero. If it's 0, we're through. That's what we want to prove. If it's non-zero, you can divide by it. If theta is non-zero, you can divide this by theta and conclude that this is equal to j. Right, so just substituting back into the original here, dividing both sides by theta, which is now constant. But that's a contradiction because this symplectic form is it can never be 0 on a global manifold. Never be globally exact on a compact manifold. Okay, so right. So the idea is to jazz all of that up a little bit so it applies to things which are a bit more exotic than one forms. Okay, first of all, in order to do that, there's a bit of machinery, and really the object of the exercise is to get something like the BGG complex working on complex projective space. And first of all, there's a replacement for the Durham complex on complex projective space, where what you do is you look at the normal Durham complex to start with, and you start taking out the trace parts. Right? So this is a symplectic manifold. These things do not correspond to irreducible representations of the symplectic group, but you can take the trace out of each of these things. So you do that for a while until you get to about half the dimension, well, until you get to half the dimension. And then, amazingly enough, there's a second order natural operator which goes between this bundle and itself, and then you go all the way back again by other first order operators. And this is very similar to the Well, it's very similar to the Riemann complex in contact geometry, but this is something you can write down an arbitrary symplectic manifold. But unlike the de Rham complex, it has local cohomology here. Well, it has local cohomology exactly like the de Rham complex here, but it also has cohomology here, and that cohomology is. Local cohomology means that, think of this as a sequence of sheaves. Or in other words, if you have an open set, what does it mean to have, if you restrict this to an open set, what is the kernel of this one modulo the image of this one? And it can be identified with constants. Right. Yeah. And then the other thing is, well, so there's this complex lying around in the background, and then the other thing is that the proof on the previous slide is really saying that this sequence is exact, right? So although there is local cohomology at this point in locally, right, globally that cohomology washes out, and this is actually an exact sequence, right? So to have a one form so that the trace-free part of its exterior derivative is equal to 0 is the same as saying that it's exact. Right. Let me just go on a little bit more with some symplectic geometry. What I'm going to do is write down a connection on CPN, which is going to be like one of these tractor connections. Okay, it's going to have curvature which is very special. Here is something that you could insist about a connection on a general symplectic manifold. You could insist that the curvature, that's the thing on the left-hand side, here is actually just a multiple, really just a multiple of the symplectic form. So this is some endomorphism, and this is some symplectic form. So this is a little bit like Hermitian Einstein, or something like that for a Hermitian bundle. So V is just some vector bundle. So you've got a vector bundle on a symplectic manifold, and you insist on this. The curvature being special like that actually means that if you take out this part where you don't see J, then this is a complex, and that actually continues on. So the whole Riemann-Seshadri complex can be coupled with this. So it really is a good analog of having a flat connection in other. Yeah. It's really like having a flat connection. It's as flat as it could be, except that you've got to take the symplectic form into account. Okay, so this is still a complex all the way up. And then there's a global result. So you can deduce from this that, in fact, the very same thing, but coupled with V, right, this is what I was saying, the uncoupled version is what I was saying about forms, where you can couple it with V and it's still exact. Okay, so there's some mild conditions here that have to be satisfied, which I'm not going to tell you about. Okay, how do you use this? Okay, so what I'm going to do now is try and jazz up the previous argument, which was for one forms, and I'm going to jazz it up to symmetric forms. So again, this same chap, Michel, is involved in showing that if you have a symmetric form, which is in the kernel of the X-ray transform, then it's actually the symmetrized derivative of a one form. It's a function. It's just a function. So the integral of a symmetric 2 form here is obtained by taking unit parameterization, take the vector and plug it into both slots and get yourself into both slots and then integrate. Right. So this is a number for each gamma. Right. You'll notice that 1973 is earlier than 1978. So he did the case of symmetric 2 tensors before doing the case of one forms, which seems absurd. But in fact, this has a geometric interpretation, so there's more motivation for doing this one. This is the infinitesimal statement of the Blaschke conjecture, which is actually now a theorem. Okay, so let's not get into that, but there's some motivation for looking at these transforms. Okay, so once you know about the BGG complex, then there's another way of saying this. You can articulate this by saying that these integrability conditions vanish. All right, now this gives you something which you can then hope to restrict from CPN to RPN. Okay, now what you'd like to show is this. This is the corresponding statement for CPN, and really the moral is that anything that happens on RPN actually has a counterpart which is true on CPN. But this is a much more difficult theorem, 1981. Tsukamoto proves this by expanding everything in spherical harmonics for the complex projective space. But you would not want to check this without medical supervision. It's really, really tough. This is a really, really tough argument. Okay, done in this way. So the whole object is to find, slick ways of doing these things. Okay, now, what you know by the curvature lemma then, this philosophy says that, in fact, what you know is that if you know this is equal to 0 for all gamma inside CPN, there's the usual trick of putting this gamma inside RPN. Right, you know that something is restricted to 0 on RPN, and then there's this curvature lemma, which says that some part of this is equal to 0. So you get some integrability condition by looking at the corresponding theorem on RPN, interpreting the result by means of the BGG complex, and then restricting the result down to C, and then making deductions about what must have happened on CPN. Okay. So what it suffices to show is that actually this is the integrability condition for being in the range of the corresponding differential operator on CPN. So what you'd like is something which is an analog of the BGG, but on CPN. And this should be exactly the integrability condition. So what about this? Well, what you do is you use the sort of ingredients of the construction of the BGG complex, and you try and do it on complex projective space. Here is a remarkable connection on a remarkable bundle on complex projective space, and I just obtained this more or less by trial and error. This is also related to joint work with Jan Slovak, where we generalize this to other symplectic manifolds. But this remarkable connection is remarkable in two ways. First of all, it does satisfy this curvature constraint, so it's trying to be flat with respect to the symplectic structure, but it's not. And secondly, if you look at this for this bundle and then unravel what it really means in terms of tensors, then you get exactly this implication that you want. Now, this unraveling involves some serious tensor manipulations, and I can't even do these serious tensor manipulations by hand, even for this case, right? So, I mean, I can prove them by dimension counting in this case, but I cannot even do the manipulations by hand. What's really going on is that there's some Lie algebra cohomology which is doing the manipulations for you. It's the Lie algebra cohomology of the Heisenberg group, or the Heisenberg Lie algebra, and it's being computed according to Costant's theorem. So it's got the same ingredients as the BGG machinery, but it's not giving you a BGG complex. It's giving you something which is related.
So what does this obstruct? The parallel sections correspond to?
You mean parallel sections of this?
Of this connection you've written down.
You mean what's the kernel? Oh, it's something very trivial. Let's see, it's isometries, in fact, isometries of the Kähler metric. Yeah, so it's so the kernel of this is a condition on a one form. Okay, yeah, I mean it's not directly that, but if you unravel it and think about it, that's what it turns out to be. Maybe. So okay, not really. So, okay, so, yes. So the joint work with Jan Slovak, which I was alluding to earlier, is how do you make sense of this on more general manifolds? And now some of these components are just, okay, so this makes perfectly good sense, but here, you recognize that this really shouldn't be just the metric anymore on a general manifold. This should have something to do with the curvature, and so should these pieces. Right? And this piece here should not just be the symplectic form. It should have something to do with curvature. just as the transition between the formulae that pertain on the sphere and the tractor connection. Okay, so you can't immediately take this formula and just whack it onto a Kähler manifold and expect anything interesting to happen at all. So this is very special to complex projective space. Okay, yeah. Right, so maybe summarize what actually happened, summarize the results then. So by getting all this machinery to work on complex projective space, then if you can bootstrap up from real projective space to complex projective space to obtain the expected result, to find the kernel of the X-ray transform on a symmetric tensor of any rank you like. Okay, so it's combining these algebraic statements about how tensors pull back from real projective space, from complex projective space to real projective space, some BGG complexes on real projective space, some symplectic geometry to get some sort of complex working on complex projective space, and bootstrapping all the way up from real projective space. Okay, so finally, let me say a few words about how you prove a theorem like this on real projective space. Okay, so as I said before, the case of one forms was done by Michel in 1978. The case of symmetric two forms was done by Michel in 1973. There's one other case done for symmetric three forms by Etzze, and say it? I can't. Yeah, that one. Yeah, and that's about it. But if you want to prove it generally, then this is the sort of machinery you can use. So you can use some complex analysis, so complex methods. Let me just draw the picture of what's going on. This is the complexified picture of the correspondence that we're interested in. So you're starting with real projective space and you're looking at the space of geodesics. If all these complex numbers, if all the complex projective space and so on here were replaced by real, this is the correspondence which is relevant to the X-ray transform. But here is the complex version where I've just replaced real numbers by complex numbers everywhere. Okay, so the one we're really interested in is this. This is the real version. And between, of course, the real version sits inside the complex version. Everything is sitting inside as totally real submanifolds, but it's not really very helpful. You want some sort of combination of the complex analysis that you have here with real analysis that you have here. And what you do is you simply take this thing here, which is real sitting inside that, and you look at its inverse image inside of this complex manifold. And on the left-hand side, so this has dimension 2n, and on the left-hand side, you just push it down to CPn by just restricting the projection mu. What happens? Well, these are both manifolds of dimension 2n, but this eta here is no longer any nice mapping. It's actually an identity in most places, but some places it goes wrong. Right, so the point is that here there's a well-known machinery for investigating things. It's called the double fibration transform. What you'd like to do is get that sort of machinery, the machinery of the Penrose transform and so on, working for something which looks like that. Okay, let me call this thing, give this thing a name F. Right, and then the point is that there's a special relationship between F and CPN. What happens is that F, if you just look at this fibration, as I said, well, look at this mapping. This mapping goes wrong some places. Most of the places it's an isomorphism, but it degenerates along real projective space. And what it is actually, it can be identified with just a real blow-up of CPN along RPN. And what happens is that F acquires some structure here, which is as sort of as close as possible as it can to try to have some complex structure. It's called an involutive structure. You can read about this in an article I wrote with Robin Graham. And And you can, by using this involutive structure as a replacement for complex analysis, which happens here, you can set up some machinery which does all this. Okay, there's some sort of philosophy here, and the philosophy is that instead of using spherical harmonics, what you're going to do is use something like the Bott-Borel-Weil theorem to organize your spherical harmonics for you. Okay, so in principle, you can prove the Bott-Borel-Weil theorem by expanding everything in spherical harmonics. I mean, only in principle. You cannot do that really, I don't think. Okay, well, anyway, this is getting a bit out of control now, and I'm out of time. There's some references here. So, for example, there's, if you want to read about this involutive structure, that's where you read about it. And that's all I have to say. So, thanks very much. Yes, Riemann.
What's this map again, and how do you?
Yeah. I mean, the interesting is what is the second order operator in the middle, isn't it? Yes. So let me. Right. Let me put this complex back on the board. Right. Let's go back a bit. Actually, there's a trick for doing this, isn't there? Yeah. Okay. Right. Okay. Yeah, so the first part of the complex here is you're just taking the trace-free part all the time. Okay, and that's compatible with exterior derivative because J is closed. The interesting thing, though, is what happens when you get about halfway along here. Now, this operator is actually a second-order operator. Right? It's not a first-order operator anymore. So, and then these things are first-order operators.
So the obvious thing would be to go to n+1 or just take star, and then you're at n-1.
Yeah, but there's no star operator.
And then go up again.
Yeah, but there's no star operator. This is on a symplectic manifold. Oh, okay, yeah, but it's not that. Okay. Yeah, I know. Okay, yeah. Right. So, So the construction of this is a little bit complicated. Let's see.
I mean, you don't have that many natural.
No, I know. Yeah. Yeah. It's not what you said.
I know that.
Yeah. But the question is, what is it? It's a bit difficult to write down. Let me do a slightly easier case, and notice by the way that this has got not got the right length to be a replacement for the de Rham complex. It's got one too many bundles in it. Let me do the corresponding thing for a contact manifold. All right, so which is slightly easier, I think. So let me do the corresponding thing for a contact manifold, and just to keep the dimensions within control, let me do it for a three-dimensional contact manifold. So for a three-dimensional contact manifold, you have a distribution inside the tangent space. Okay, rank 2. Okay, or equivalently, what you have is a line bundle inside the bundle of one forms. Okay, so dually, you have a line bundle inside the bundle of one forms. Let me now write down the de Rham complex. So 0 forms to 1 forms to 2 forms to 3 forms. D. That's as far as it goes since we're on a three-dimensional manifold. Here you've got a line bundle sitting inside here. And it has a quotient. And I'm going to call the quotient 1 forms in the D direction, if you like. Okay, so these are 1 forms in the contact direction. Okay, as a consequence of this, just an algebraic consequence of this, of course, you have a mapping from here to wedge 2 of D. Right, so this is just this wedge itself, which is a line bundle because this is rank 2, so this is a line bundle. And here what you have is 1 forms in D tensor L coming in. Okay, so now you've got this diagram. Okay, now if you go from here to here, then this is looks like a differential operator, but it's not. Right? This is actually another way of saying what the Levy bracket is. This is the obstruction to Frobenius integrability. Okay, so if you've got a contact manifold, that's where this is not integrable, then this is actually an isomorphism. Okay, and it's just an algebraic isomorphism. Right, now you can define your second order operator, right? Because what you do is you start with something in here, right? You make an arbitrary choice here, you lift it arbitrarily, and you see what happens if you go from here to here. And when you go from there to there, well, you might get something which is, well, what you do is you go from here to here, which is one differential operator. Then you use this isomorphism to go back to there. And then you come back here and do this D again. Right, so that's what it is for the contact case. And then by diagram chasing, you can check that even locally, it's even better than this case. You can by diagram chasing, you can check that being in the kernel of this second order operator from here to here then is exactly the same as being in the range of this composition.
So in this one, you have to choose a lift to the range.
You have to choose a lift to the yes. So something washes out, but yeah. Yeah. You'd think so, wouldn't you? Yes. There's a relationship, but the question is whether there's a helpful relationship. Right, so what one might try and do is, instead of doing this on complex projective space, do it on the sphere, which is above it with its natural contact structure. Okay, I did not, I can get that to work, but it's not as nice. It's not nearly as nice. No. So you can exploit the BGG complex exactly on the sphere. But the trouble is you have to do some integration along the fibers all the time to relate things backwards and forwards. It becomes a bit messy. Yeah, but yes, that's right. Yeah.
So when you talk about the function transform, you look
Yes.
at going from even functions to even functions.
Yes.
And you want to interpret it invariantly, so you put in your line models.
Yes.
Why did you get odd things? In the image space, even turned into odd when you did it. You had the E tilde at -1. So how did something odd show up?
No, but it's -1 as well. So both of those are, both of those are getting you back to yeah. There's two minus signs in effect. Yeah.
Let me take this opportunity on behalf of all the participants at the conference to thank you for a wonderful series of lectures. Man, you've really seduced us with the beauty and the power of the Projective geometry, its applications, conformal geometry, and showed us many model geometries. And I think you've also provided a wonderful model on how to give a series of 5 lectures. Thank you very much, Mike.
Thank you.